foreseen to exclusive reading tickets.
Good. So our next speaker will be Janardhan Kulkarni, postdoc at MSR right now. Talk about flow time.
Thanks, Nikhil. Today I'm going to talk about online flow time optimization for unrelated machines. Most of the basics for flow time optimization was already covered by Kamesh. And he presented an algorithm, proportional fairness, which sort of gives fairly good algorithm for a large class of scheduling problems. But one special case, when I say special case, don't take it as it's in a narrow sense, but an important special case of this problem is unrelated machine scheduling, and for which the algorithm presented by Kamesh does not, at least as of now, we don't understand whether it performs well. And that special case is unrelated machines, which was introduced by Lenz Tashmash and Tardosh, who is there in the audience. David Schmois is in the audience. And so what's the problem? Here we are given a set of machines and a set of jobs, and the reason we call it as unrelated is that the properties of the jobs, in particular its processing length, depends on the machine. Okay? So for example, if there is a job J, it may take 1 unit if you schedule on first machine, it may take 10 units if you schedule on second machine, and so on. Okay? So that's the reason why we call it as unrelated machines. And although this model was introduced in '87, it is still relevant even in the current scheduling applications. Think of it as maybe if the job has the data located on a particular machine, then it takes shorter duration to complete, and if the data is not located, then you have to fetch the data, so then it takes a longer duration to complete. So the model is highly relevant even in today's applications. And the way we formalize it as the follows: we think every job has a processing length, Pj, and this is the amount of the work job needs to do, but it has a speed Sij, which depends on the machine and the job I. Okay, so if you assign the job to machine I, job J to machine I, then it runs at this speed. The speed is some quantity between 0 to 1. Okay, and the processing length, I will use this notation Pij is Pj over Pj divided by Sij. Okay, I will switch back and forth between these two the notations. But for conciseness, we will use Pij to denote the processing length of job J on machine I. Okay? And what is the unrelated machine scheduling problem? We are given the set of jobs and set of machines, and you want to assign these jobs to minimize some quality of service. And this is perhaps the most well-studied model in scheduling theory and even in approximation algorithms. It has not only practical relevance, but it's also sort of a textbook stuff in design of approximation algorithms. So for example, the Lenz Tashmash rounding in 87 is really like the prototypical application of LP rounding. And some of my favorite results in the recent years, like for example, Bansal, Maxim's result on Santa Claus rounding, and the Santa Claus for unrelated machine rounding by Ola, they're all studied in the context of this problem. So both it has practical relevance, but it is arguably the most fundamental, the model in approximations and scheduling theory. Okay, and in this talk, I'm mostly interested in understanding the flow time objective, the objective which was already defined by Kamesh. And as I already told, the algorithm which was discussed in the previous talk doesn't actually give any meaningful guarantees for this problem. Okay, so what's the plan? The plan is to like sort of so discuss the two algorithms which give you meaningful competitive ratios for this problem. The one algorithm by Chadha, Garg, and Kumar, who is Amit Kumar is in the audience, and another non-clairvoyant algorithm by Sungjim and myself and Kamesh and Kirk Bruce. And we will see the analysis of these algorithms via the lens of duality. The Kamesh proposed, Kamesh showed a potential function-based analysis, but I will show a duality-based analysis. And then I will briefly touch upon some connections to equilibrium concepts and yeah.
Is preemption or migration allowed?
Yes, so I will briefly tell you, yes, both preemption and migrations are allowed. Just to recap, what is the flow time, completion time minus the release time? And you can also represent the total flow time of the job as the number of jobs which are alive at time t. So this quantity will be useful in the analysis. So this is the formula to keep in mind. And this problem has a long history, starting from 1996. The problem of the minimizing flow time has been studied both in offline and online settings. I don't want to go into details, but one thing to note is that many of the earlier result applied only in identical machines, related machines, and restricted assignment setting, but not really in the unrelated machine setting. The results for unrelated machine settings have been only recent work. And the reason for this is the flow time is a very brittle objective. Like if you perturb the input by a bit, then the objective function completely changes, and this poses a lot of technical challenges in the analysis. So for example, even in the offline setting, we did not know any approximation algorithms for unrelated machines. It was recently was given in my work with Bansal. But today, of course, I'm only going to talk about online. And in the online setting, it's you know about the job when it arrives. Okay, so the set of the machines are already given to you, and when the job comes, you learn these two parameters, Sij and Pj. Okay, so the goal is to assign to minimize average flow time or the total flow time. As someone asked earlier, so what are the assumptions we are making? We assume that the jobs can be preempted. On a single machine, the scheduling policy can preempt jobs. This is necessary. Without that, you can't get any meaningful results, even in the offline setting. And the jobs can also be migrated. You mean the jobs can be processed on a machine for some duration of time, but you can switch this assignment over the course of its execution. But the important property, you might be thinking, and then what else is left? So important property is that at any time, you are assigning job to only single machines. That's the most crucial thing. So physically, you can't process the same job on multiple machines. So that is not allowed. Okay, and we do the standard competitive analysis where we measure the cost, worst case, the cost of the algorithm. And in particular, for flow time problems, you can't without this what is so-called resource augmentation or speed augmentation, you can't get any meaningful guarantees. So we compare ourselves with the algorithms which have 1 + epsilon speed, whereas the opt is restricted to the speed of 1. Okay, so this is mostly for the sake of analysis. Algorithms themselves don't depend on this thing, so that's a nice thing. This is a purely an analysis technique. Okay. Any questions so far? So this is the problem we are going to study for this remainder of this talk. So we are given a set of unrelated machines. The jobs have Pij, the value Pij on it, and the goal is to the design algorithms which are good for the flow time objective. Yes?
Can you give some intuition why this resource augmentation is useful?
So the way I think resource augmentation is separating between good algorithms from bad algorithms. In the worst case analysis, if you do a worst case analysis for these problems, all algorithms turn out to be equally bad. So they say that competitive ratio of any algorithm cannot be more than n, for example, or of n. So then, but then clearly we observe that some algorithms are better than the others. And how do you separate good algorithms from the bad? So I will give you some extra resource. Then some algorithms perform significantly better than the other, and that gives a good separation. And for me, analysis is all about which algorithm is better than the other. So that's one. There is also queuing theoretic motivation for it, but I don't want to get into that. Okay. Any other questions? Okay, so first, I will present the first online. Oh.
Do you assume that migration is free?
Yes, migration and preemptions both come at no cost. Okay, but we will see that we don't migrate too much. I mean, we can bound how much we migrate. So, okay. So I will quickly want to review this very elegant algorithm by Chadha, Garg, and Kumar. I'm citing two things. This algorithm was proposed in a stock paper in 09, but it was a more elegant proof was given in Soda result by subset of the same authors. And the algorithm, this was the first algorithm for the unrelated machines in the online setting. And so if you think about this problem for a bit, what are the two decisions an online algorithm has to do for minimizing flow time? So you have to take two decisions. One is, if I tell you the subset of the jobs assigned to a machine, how do you schedule them? And then another decision you need to take is, what are the subset of jobs which go to a particular machine? So there is an assignment, the decision you need to take, and there is a scheduling decision you need to take. Okay, so these are the two important decisions an online algorithm has to make. And if you are familiar with this literature, then the first question is not too difficult to solve, because on a single machine, if you want to minimize flow time, and if you recollect, the flow time is just the number of jobs alive at a particular time t. So then basically you want to finish the jobs as quickly as possible. So one way to, loosely speaking, what you want to do is to schedule smaller jobs and you finish them fast so that the number of jobs remaining at a time is small. Okay? So the shortest remaining time first is sort of a good rule. But the crux of the most of the algorithms, including the algorithms I'm going to present today, is the assignment. What are the subset of jobs which go to the machines? And this is a really difficult question in the unrelated machine settings because the jobs have really different characteristics on the machines. Right? Okay.
But you allow migration.
Yes.
So you might reassign.
Yes.
So I mean,
So,
the same machine policy only has one job at a time.
Yes, yeah. This algorithm by Chaddag and Kumar really doesn't need migration. So I'm presenting two algorithms, one clairvoyant and one non-clairvoyant. So this algorithm doesn't need, so this rule is well defined. Okay. And it's what is the assignment policy? And in this paper, they proposed the following very simple looking assignment policy. What they say is that since I'm already scheduling jobs based on the SRPT rule, it gives an ordering of the jobs on a particular machine. When a job comes, you just assign, you pretend you do this thought experiment. I will assign these jobs to different machines and see how much the flow time increases. Because the first rule is already fixed, you can calculate this quantity. And they say that, okay, assign this job to the machine which increases the objective by the least. So it's a greedy policy. And this is a one-shot assignment. They never change the assignment of the jobs. But this crucially needs the knowledge of the processing lengths because the SRPT rule itself needs the processing length of the jobs. It's a brilliant algorithm. I mean, if you see the literature before this algorithm, it was quite complicated. And they came up with a, OK, so let me just illustrate if it was not clear. Suppose this was the queue of the jobs on the two machines. When a new job comes of the length 20, you just assign it to the first machine. Then you can calculate the increase is 31 plus 20, which is 51. And if you assign the job on the second machine, the increase is 68. So you will choose the assign the job to the first machine and execute in the shortest job first order. Okay. And they show that this algorithm, what I call it as a greedy algorithm, is 1 plus epsilon speed, 1 over epsilon competitive for minimizing total weighted flow time. So initially, they gave a very nice potential function argument. And in the SODA 12 paper, they even give a more sophisticated dual fitting argument. And both of them are extremely nice, and I highly recommend reading them. Okay? But one, I wouldn't say a drawback, but the limitation of this algorithm is that it crucially depends on knowing the values of the PJ. And by that, I mean, even if I give an estimate of the PJ, I don't know exactly what's the value of PJ, but it may be between 2 PJ to 4 PJ, then the algorithm needs more speed. So it is not graceful in that sense. And estimating the values of PJ is a really difficult problem in real world applications. So one of the important problems in the online flow time literature was that can there be an algorithm which is non-clairvoyant, which does not even look at the values of the PJ, but it knows the values of the Sij, the speed of the job on a machine I, and still get a good competitive algorithms. Okay, and we show in our work that there is such an algorithm indeed, and we call it a selfish migrate, and it almost achieves the same guarantee that if you give me 1 plus epsilon speed, we can show an algorithm which is 1 over epsilon square competitive. In the full information setting, it was 1 over epsilon, and in this non-clairvoyant setting is 1 of epsilon square. But pretty much, except that it's the same, it matches the bound. But there is one important difference. Here, the migration is necessary. Someone was asking me this before. So here, the migration is necessary, and without migration, you can't achieve any meaningful guarantees. Okay, so this algorithm actually reassigns jobs over the course of its execution. Okay, I would again, so there are, even in the non-clairvoyant setting, there are two decisions to make. So let me describe what is the algorithm. So the first decision is the scheduling policy, and the scheduling policy itself has to be non-clairvoyant now because we don't know the processing length. So the scheduling policy on each machine is the simple round robin algorithm. Okay, so I'm cheating a bit here because round robin actually does not give you 1 plus epsilon thing, but it's a modification of round robin, but it's not too much of a modification. Okay, and if you don't know what's a round robin algorithm, it basically shares CPU equally among all the jobs. Okay, if there were n jobs at a particular time t, then it assigns 1 over n fraction to each job. Okay. So, but the crucial thing, which was like the bottleneck for designing algorithms in the non-clairvoyant setting, is what is the assignment of jobs to machines. Since you basically don't know the processing lengths, and the flow time is so much dependent on like assigning, calculating these quantities, like the increase in the objective, it was not at all clear what is the good assignment of the jobs to machines. And we overcome by doing this following thought experiment. We basically set it up as a game. Okay, so we think that, okay, every job is trying to minimize its own flow time, and it sort of tries to assign itself to the job, to the machine, which sort of gives it a good rate. Okay, I will make it precise, but the overall thing is that we don't explicitly calculate the assignment. We set it up as a game between jobs and machines, and an equilibrium outcome of this game will be assignment of the jobs to machines. Okay. For that, I need the notions of virtual queues and job behavior. I will describe it in few slides. But I want to pause for a bit and tell that this is all just for the assignment. Okay. So the scheduling policy on each machine is already fixed. I'm going to do round robin, but I'm setting up this as a game just to find the assignment of the jobs to machines. Okay. So what is to define this game? I need the notion of queues. Every job maintains set this queue over jobs. It's basically a FIFO queue. Okay, every job which wants to move from one machine to another is free to move, but if it moves, then it has to go at the end of the queue. Okay, so in our algorithm, the jobs can migrate at any time. It's like the job decides to move from one machine to another, but whenever it moves, it has to go at the tail. So we let the jobs to migrate at any time. Okay, but what is not allowed is like if the job moves to another machine, it joins in the middle of the queue. So that's not allowed. So basically, it behaves like a FIFO queue. Okay, and now why do jobs wants to change machine assignments? It's based on this quantity what we call as virtual rate. So every job wants to maximize this virtual rate. If you think this as the utility of the jobs basically, and this quantity is basically the speed of the job on the machine I divided by the position of the job in the virtual queue. Okay, so this is sort of a proxy for how much rate this job gets on the machine I. Since we are doing round robin, this quantity is related to the number of the jobs on that machine. So this is proxy for how much rate I would get if I move to the machine I. Note that if this was NT, which is number of jobs at time t, then it would be exactly the rate the job gets. But this is not quite the same. But that's the intuition for this rule. So see, if the job gets executed faster at a particular time, its own flow time minimizes. So that sort of is the intuition for why every job wants to minimize this, maximize this quantity. Okay. So this is the virtual rate of the jobs, and every job wants to get assigned to the machine which maximizes this virtual rate. Okay. So for example, if the job J was on machine 1, the phi1 jt at time t will be like 1/3 s1j by 3 because its position is 3 in this queue and its speed is s1j. But if it can move to the machine 2 if it wants, but then its phi will be this quantity because it has to go at the tail of the queue. Okay, so the algorithm sort of implicitly defines this game where every job is trying to maximize this the virtual rate. Okay, so what is the assignment? So the assignment is the outcome of this game where each job chooses the machine which maximizes this quantity simultaneously. What it means that as an assignment is valid in my scheduling policy if at this current configuration of the jobs, every job is assigned to the machine which is maximizes the quantity. Okay, maybe or in game theoretic terms, this is basically the Nash equilibrium if I took this as the utility of the job. Okay, but some of you might be like worried at this point because it's not clear a priori why such an equilibrium outcome should exist at all. So is this algorithm well defined? It is well defined if I show that simultaneously everybody can be assigned to the machine which maximizes this quantity, right? In other words, there is a pure Nash equilibrium for this game. And that is fairly easy to prove. Suppose at time t there is a Nash equilibrium. If no event happens, no job comes or leaves, then at time t+1 there will be an equilibrium. But there are two events which can change this quantity. That is the arrival of a job or a departure of the job when the job completes. The arrival is not at all a problem, because when a job arrives, it goes at the tail, and the way this quantity was defined only was dependent on the jobs which are ahead of it. So this quantity for the other jobs does not change at all. So that still will be a Nash equilibrium. So this is fairly simple. But the more interesting thing happens when a job completes. Suppose a job completes here, then the queues get sort of rearranged, and my phi quantity keeps changing. So maybe job starts deciding to move from one machine to another, and so there will be a best response dynamics. That's what we call in game theory. So the jobs can keep changing the assignment, and I want to show you that this actually converges. This cannot keep on going forever. And that also follows from fairly simple observation, because why did the job move? A job moved because its phi jt increased. So its virtual rate increased. But when it moves, it always moves at the tail, so it does not change the phi values of the other jobs, so there nothing changed. And in the queue it departed from, they sort of slide in, so it can also go up. So whenever a job moves, it keeps growing. So the Nash equilibrium exists. You just take this as the potential. In fact, this is the potential game, so there will always be a Nash equilibrium. But there is another important crucial fact which will be used in the analysis, is that the virtual rate of the job, not just in the assignment, but in the entire course, only keeps going up. It monotonically keeps increasing. It never decreases. And this monotonicity is important for this analysis. And if you try to connect to the previous talk, that was the thing which we did not have in the PF allocation for Leontief utilities, for example. So the monotonicity somehow plays an important role. It's not that, yeah.
I'm a little confused because I thought the order on a machine is the round robin order.
Yes, that.
So it's not that the job is completely finished when it goes back in the line, right?
No. So this is just to figure out what is the assignment of the job. So I'm just defining how the jobs are assigned to machines. So once you give me the assignment, every machine is scheduling based on round robin.
Yeah, but why does the virtual rate of the job always never going to decrease? I mean, if it after it runs for a while, it put in the last in the queue.
Yes, but the point is that's the way we define this quantity, because so if suppose the job was assigned to some particular machine, let's say this, right? If it sticks to this machine itself, it never changes its assignment, then what can happen is the front of the queue starts depleting, right? So then its virtual rate only goes up, because the way the quantity virtual rate was defined is basically this n over t, which is the number of position of the job in the queue, right? If it just stuck to the machine it was in, this quantity would not have decreased. No, so that was the crucial thing, yes. So this is just to figure out the assignment. It's nothing to do with the way jobs are processed. Okay, good question. All right, so basically we proved that the Nash equilibrium exists, and in particular we need this for the analysis. So in the rest 10 minutes I will give you the proof of how these algorithms are analyzed, and these algorithms, both the greedy algorithm and the So there were two components to the scheduling algorithm. One was the assignment of the jobs, and another was how the jobs are scheduled processed on a particular machine. So the jobs are processed using round robin. It has nothing to do with queues and how jobs migrate at all, right? If you tell me what are the subset of jobs that are assigned, we just use the round robin to schedule them. But the way to figure out the assignment of the jobs, we did this thought experiment where we set it as a game between jobs and machines, and which all dependent on this virtual rates and so on. And the outcome of this, a Nash equilibrium of this game will give me an assignment. Okay,
so intuitively, to understand, I guess the problem is, you assign a job to some machine, but you don't know the sizes, right? So this queue that looked bad, I mean, it could become very good. Maybe they're working. And that's why you want to move.
Yes.
Yeah. That's your rule.
Yeah, exactly. Yeah. So because if some machine starts looking good, the queue sort of decreasing, then I want to start moving jobs to those machines. So this is one way to do it. Yeah.
So just to make sure, right now, according to this rule, a job might
oscillate madly between two queues if one guy decreases.
Yes.
So right now there's no bound on the number of migrations, but maybe you'll do something.
Yes, okay, so let me, I don't have that thing here, but we can show that every job in its entire course does not migrate more than log p, log of some processing length. So the reason is very simple. Instead of moving whenever my rate increases, I will move only 1 plus epsilon rate increases, then that basically solves the problem. Okay? Any other questions on the algorithm? All right. So, so I will present an analysis, or I will try to sketch the proof of this these algorithms using duality. So this is another analysis technique which has been dominant in analysis of scheduling algorithms, and the potential function is one of the main tools we use, and the duality has recently duality has been also been used to analyze the algorithms. And the way to analyze is fairly standard, which is common in approximation algorithms. You formulate the problem as an optimization problem, and you write the dual, and we know these inequalities and how the primal, dual, and the opt relate. And you basically try to show that since I already have an algorithm, you try to produce a dual feasible solution which sort of ties with the cost of the algorithm. Okay, that is fairly the idea. So for this primal, the LP is basically the one to minimize the flow time of the jobs. I don't want to get into too much details because we don't really use the primal LP too much. But there are two natural constraints. This first constraint basically says that the job has to be completely processed. And the second constraint says that at any time on every machine, there is only 1 unit of the job being processed. And this objective function is somewhat non-trivial because we can't write completion times or flow times as a linear objective, but this gives a lower bound. I don't want to get into the details, but it's also called as fractional flow time. But this is fairly standard, and it has been used in several other places. Okay, and the dual has this nice structure where there is one variable alpha j corresponding to this primal constraint that every job gets finished, and there is one variable beta it which basically corresponds to the second constraint. And the dual has this following form. Where you want to maximize summation over alpha j minus summation over beta it subject to this constraint. So let me zoom this in, where for each machine, for every job, for each job and each time slot, there is a constraint. Okay, so there is one variable alpha j, and this quantity which needs to be satisfied at every time t for every machine. Okay. And both the greedy algorithm and the selfish migrate algorithm I proposed have some common characteristics. They interpret beta it as the number of jobs alive in my schedule, okay, or the total weight of the jobs alive in my schedule. So then if you set beta it to be that, this can also be re-derived using primal dual methods, but I'm just presenting as a dual fitting idea. Then this term in the dual looks like the total flow time, because recollect that the flow time is basically number of jobs alive at time t. So if I set beta it to be this parameter, then this objective is the total flow time. And somehow you also want to say that alpha j, I can set it in such a way that the first term is also approximately equal to the total flow time of the jobs. And if you did, basically you give okay, I mean, if you exactly prove that it is equal to the total flow time, then the dual objective is 0, which is meaningless. But then you use some scaling tricks, which is common in approximation algorithms. And here, the scaling also depends on the speed, actually, the speed of the speed given to the algorithm, and that is very crucial. Without that, you basically can't show any positive dual objective. Okay, so but that will be the plan. You want to set the total. You want to set alpha j as roughly corresponding to the total weighted flow time of the jobs. Okay, and if you think about bit in the proof of Chadha, Garg and Kumar, or Anand, Garg and Kumar in the Soda paper, they set alpha j to be the increase in the dual objective when a job arrived, and that is quite natural because this quantity pj times beta it is basically the number of jobs, and it's my processing length on the machine I, And if you think, if in the SRPT rule, when I insert a job, the amount it increases is exactly my length times the number of the jobs, because all the jobs ahead of me were at most my size, and that all the jobs behind me will push back by my processing length. So this quantity looks exactly this thing, and they basically argue that if you set this, then the dual constraints will be satisfied, and the primal objective will be like 1 over epsilon times the cost of my schedule. You can also interpret it by primal dual analysis, but this is the main observation. But the things become a lot more tricky. Okay, so if I did that, then it's the cost of the algorithm. So we also want to do the same. We want to relate this alpha j to the cost of my schedule, but it becomes a lot more tricky in our case since we don't know. We don't have a good handle on how alpha j behaves. So that's the crux, but I will try to now give a proof of how we set our alpha j variables. And remember, what we want to show is that, so alpha j is approximately related to the cost of my algorithm, but more importantly, I also need to verify that this alpha j, all the constraints are satisfied. I mean, the way I want to think is that there is one variable alpha j, but there are constraints corresponding to each machine. Right? So you set this variable, but at every time you want to simultaneously say that these constraints are satisfied. To define alpha j, we need two quantities, which is which we denote by delta 1. So the delta 1 basically is, so at time t, there is a job j, and you think the presence of this job hurts other jobs, because of this job, some amount of the processing unit is given to this. So because of this job, every other job gets slowed down, right? I mean, so the presence of the jobs take away the CPU from other things. So, so what we want to measure is that the delta 1 of t at time t is the total increase in the flow time the job j causes on other jobs in its entire course of the schedule. And the first lemma we show is that this quantity is sort of inversely proportional to the phi. Right? And this is one intuition which everybody saw, every job was trying to maximize this quantity. I want to keep this quantity smaller because I want to keep my dual objective is small or the flow time to be small. So I want to keep this quantity small, which means that I want to maximize this quantity. So this is one motivation to define this game. And this proof of this crucially uses the monotonicity of the phi function. Okay, and the second the term we need is the delta 2 of t, which is basically the total increase in the flow time the job has caused till now on other jobs till time t. You fix a time t, then you look at all the previous time steps, and you see how much this job made slowed down the other jobs. Okay, and we show that delta 2 of t is at most wj times t minus rj. So, and both of these proofs needs the monotonicity of the phi function. Okay, and now we define alpha j basically equal to delta 1 t plus delta 2 t. But you might be like, okay, confused a bit because this delta 1 and delta 2 have t as a parameter, but alpha j is independent of that. But we could show that for any time t, this delta 1 of t sort of keeps decreasing, and alpha j at all times we can show that this is at most this quantity. Okay, and now how do I prove that this constraint is simultaneously satisfied? And here we use the Nash equilibrium idea. So basically, so the alpha j, if you think of each constraints as a strategy, I was trying to minimize alpha j, and the alpha j is minimized and the phi j t is maximized. So since every job was on a particular machine which maximized this phi j t, so this constraint is tight for the machine on which it is assigned, and it has a slack on every other machine. So this is roughly the Nash equilibrium condition, and that again pops out of the dual constraints. Okay, so that basically completes the proof, and I think interesting takeaway from this is the interplay of like this equilibrium ideas which come out of the duality constraints And this is not a coincidence. In some sense, there are other places where we could use this exactly the same idea and show good algorithms. For example, in particular, the another line of work which has been popular in scheduling theory is to minimize flow time plus the energy, and almost the same algorithm works. And recently we extended some of the results, these results for multidimensional setting, the setting which Kamesh presented earlier. Okay, so I have one minute. Okay, so I just want to tell one more. I want to make one more comment regarding connections between equilibrium and ideas and duality. Is that so? The way we set this up as a Nash equilibrium as the outcome, and we analyze the quality of the Nash equilibrium, here it was all for the sake of the coming up with an algorithm, but there is an entire literature which sort of tries to understand the quality of the Nash equilibriums, and that's the price of anarchy analysis. And perhaps we can also use the same technique, the duality technique, to bound the price of analysis, where we write the primal program, and we try to relate the cost of a Nash equilibrium with the cost of the produce a dual certificate. And so in fact, this analysis has been used in our work, and I think this is also a good sort of like a unifying way to look at these things, like the duality arises out of the equilibrium conditions, and or in the other way, like the equilibrium conditions out of the duality constraints, and they help in the design of the algorithms. And that's it for them.
Maybe one quick question. If not, let's thank Janardhan.